So, what do we have? We have spare flanges, these ones, and they connect vertical lines, which we call spar webs. These are your spar webs, with these skins. These are your skins. And at any junction where you have these spar flanges connecting spar webs and skins, we're going to be locating booms. 1, 2, 3, 4, 5, 6. Now, booms carry direct stress. And skins shear stress. So, now, for the sake of the question, say that these spare flanges have area of 300 millimeters each. And that, you can see because of symmetry actually, this symmetric axis, that the area of boom 1 is going to be the same as boom 6, boom 2 the same as boom 5, and boom 3 the same as boom 4. So we can just look at the top of the axis and find the boom area for 1, 2, and 3. And due to symmetry, we've automatically found it for 5, 6, and 4 at the same time. So, your formula for boom areas. In standard, you'd be using this. So, area of boom is the thickness multiplied by the length, or height, or whatever, over 6. And then 2 plus direct stress ratio. Something important to remember with the direct stresses, you know that stress is going to be directly proportional to y. What is y? Y is the distance from the neutral axis to the boom you're looking at. So instead of stress like this, you can use the equivalent using the height. 2, 1, 2, 1, because it's ratios. So this you'll see is handy later. Okay, so we said we're finding the area for boom number 1. So we have to take into account this formula for any adjacent skins you have. So at boom 1, adjacent skins would be from 1 to boom 6 and from boom 1 to boom 2, plus the area of the spare flange you have. So we just said that the area for boom 1 is going to be the area contribution from the spare flange, 300 millimeters, plus we have 300, thicknesses 3 millimeters. Our value of B is going to be 400 millimeters, and we divide that by 6. So 3 times by 400 over 6. In the bracket, 2 plus the ratio for stress, which we said we can write as a ratio of the distance from the neutral axis to the boom. So, in this case, from, what are we doing? Y2, Y1. We're not looking at boom 1 to boom 2. We're looking at boom 1 to boom 6. So in here, instead of 2, we're going to be having 6. So, like this, which is y6 over y1. What is y6? This distance going down. So from the neutral axis is going to be minus 200, half of this. And up to boom 1 plus 200. So you do minus 200 over 200 millimeters and you get minus 1. 2 plus minus 1 means you're going to have 2 minus 1 in the bracket. Yeah, and then that was the contribution due to this adjacent part. What else do we have adjacent? This part. So now it's already written in terms of thigh 1 and thigh stress 1, stress 2. So in terms of ratio, we just need this distance, which is going to be y2. Here. So this distance. You know this distance is half of 400, so 200. This distance is half of 200, so 100. Between 200 and 100, because this is in the middle, from symmetry you can say it's 150. I mean, you know it's 150. And we're going to have to divide it by the value of y1, which is 200. So you have 150 over 200 in the bracket. Keep this in mind while we write this part down. Your thickness in this case from beam 1 to beam 2 for this skin is 2 millimeters, which will be times by the value of B of 600. So 2 times by 600 over 6, 2 plus, we did the bracket earlier, 150 over 200. That's that. And you're going to get like 1050 millimeters squared. And we already know that beam 1 is the same as beam 6 for the area. So 1050 millimeters squared from this. Okay, next up, beam 2. Once again, let me just get rid of this. So, the area for beam 2 is, once again, the contribution to any adjacent skins or anything you have. So in this case, at beam 2, you have the contribution for the skin from 1 to 2, or 2 to 1, 2 to 5, and 2 to 3. Plus, let's not forget the area contribution from the spare flange. We have 2 spare flanges at boom number 2. And if the area of one spare flange is 300, we're going to do 300 times by 2 because we have 2 spare flanges. Now, the contribution for boom 1 to 2 in between that one is going to be the thickness, which is 2 times by B over 6. 2 plus, we already know from earlier that for beam 1 to 2, it was 200 over 150. Last time for beam 1, so this is beam 2, we did it the opposite way. We did 150 over 200 because we are looking at beam 1. But now we're looking at beam 2. So you have to inverse this. So it's going to be, for boom 2, you have to do thigh 1 over thigh 2. So thigh 1 is y1, thigh sigma, stress. So y1 over y2. y1 is this, y2 is this. So y1 200, y2 150. So 200 over 150, the opposite of the previous one. So that's that. Next up, we have another contribution for, we've done this one, we need to add the contribution from this one. So the thickness, 2.5, thickness 2.5, the distance is of the beam, the length of the beam is this, so between 400 and 200 you're going to have 300 millimeters, so 2.5 times by 300 over 6 is the formula, 2 plus the ratio. What are we going to write inside for thigh 5 and thigh 2? Well, you can see they're symmetric, so this is y2 and y5. Just be careful which way around we're doing the ratio. Because we're looking at boom number 2, here it was 1, so 1 went on the denominator. Now we're looking at 2, so 2 goes on the denominator, so y2. And the other value of the boom you have on top, so y5. So y5 is 150 and 150, basically half of this 300 length. But 1 is negative, the 1 going down to 5. So minus 150 over 150 is minus 1. 2 plus minus 1 is minus 1. Okay, and now we have one more contribution to add. We've done this, 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 so it's just this one left from boom 2 to 3. What do we have from boom 2 to 3? Once again, thickness 1.5, the length 600, over 6 in the bracket 2 plus the ratio. We're looking at boom 2, so you put the value of y2 on the denominator and the one from the adjacent end, y3 on top. So y2 and y3. y3 is half of 200, so y3 is 100. y2, 150, because it's half of 300. So 100 over 150, you write in here. And this is going to give you B2, which is the same as B5. Plug that in your calculator and you should get 1791.7 millimeters. Okay, now we have one more to do. Okay, so last one, B3 and B4, because they're symmetric. What's going on? The area from the spare flange, once again, 300 millimeters, plus the contribution of the thickness times by the length, over 6, 2 plus, now because we're looking at boom 2 to 3, let me get this, boom 2 to 3, so between boom 2 and boom 3 is a contribution, and let me write it like this, boom 3. So adjacent to boom 3, you have between boom 3 and boom 2, and between boom 3 and boom 4. So let's do the contribution for this one, between 3 and 2. So if it's for boom 3, and 3 would be here, and between 3 and 2, you still have a 2. So theta, phi 2 over phi 3 is y2 over y3. y2 is going to be 150. y3 is 100. So you do 150 over 100 plus the contribution of this part. So thickness is 2 millimeters times by B, which is 200 over 6 plus 2 plus. Now for this, because we're at boom 3, instead of boom 1, you write this. And our other end is not 2 in this case, it's 4. So we need the ratio of y4 over y3. y4 is minus 100. And y3 is plus 100. So minus 100 over plus 100, you get minus 1. 2 plus minus 1 means just minus 1. And you can see here, boom 3 is the same as boom 4 in terms of area due to symmetry. So finally, in your calculator, and you get 891.7 millimeters squared. And that's it.